Hi everyone, welcome to Quantum Computing Fundamentals, which is what the goal of this uh, Santa Clara Quantum Meeting Group is. And this is organized by myself, Prakash, here, and my colleague, host, Professor Gokhale there. Hi,
Hello.
Gokhale.
Hi.
So, two of us welcome all of you to the 18-week course in quantum computing fundamentals, 1.5 hours every uh, Tuesday, and this is uh, by Pacific Standard Time, Pacific Daylight Time (PDT), and accordingly it will be Wednesday morning. Sorry, it will be Tuesday morning, Monday night, and Tuesday morning, approximately. The times will be somewhere in the night here, whereas morning here. So it is on 18 weeks, 18 Monday nights and Tuesday mornings. So with that, let me first of all acknowledge the valuable time all of you who joined here are. We want to be very valuable to you to accomplish whatever goals you may have as a basic, intermediate, or as a advanced learning in quantum computing fundamentals on your own, do it yourself types. We have some uh, information already provided to you, and we look forward to working with you. So let me first start with the slides. So I'll move on to the slides, and hopefully we'll be able to deliver within next 45 minutes to 1.5 hours. Uh, Two of us can get you through the earliest first starting. So here I go. Gokhale, can you see the slides now?
Not yet, Prakash.
Okay.
I
Or
think I need to stop sharing. Yeah.
oh, okay. Okay, go ahead. Stop
Okay.
sharing. Then I'll have to
Yeah,
start
I did.
sharing.
Yeah.
Yeah. Okay. So let me start sharing. Share, share screen, and then I'm going to share the slide. Okay. Share. Are you able to see the share now?
Yes, I can see. Can you just
Okay.
go to
So I'm going to
presentation
full
mode?
screen now. Yeah, I'm
Yeah.
going to presentation.
Thank you.
Hi everyone. This is quantum computing fundamentals. QCF 101 quantum computing fundamentals. That is what today it is 29th May, and having already acknowledged your time, we want to do it at a pace which is comfortable at the same time productive to it. So the quantum computing and learning room appearing here, and I am a part of the Emerging Open Technology Foundation UOTF team. So both of us, myself and Gokhale sir, both of us were from IIT Bombay alumni. So we are master's batch. I'm from electrical and Gokhale from computer science. Together, this forms a group which covers both the uh, academic as well as industrial uh, areas. Myself, I have been in the industry for 40 plus years. So is Gokhale. Both of us started differently. He started as an academic. He also started as industry, then went to academic. Same with me, and then later on, I have spent most of time in the Valley, Silicon Valley there, whereas he is 20 in Mumbai. We have past coordination for the Java Enterprise Edition, which we did for education for the uh, Sun computers, and that is how we have been working together. And in this course, what I want to say is um, both of us have the necessary qualification to encourage and motivate you to achieve what you want to do. So the course organizer, as we are part of the Emerging Open Tech Foundation, and it's a social purpose organization, and mantra, or what we call the uh, focus is on the transformation through technology. So we focus on emerging technologies It includes digital operational knowledge and quantum transformation is the new pillar we are directing now. So we have been working 4 to 5 years now, 5 to 6 years approximately, as open technology forum, and then we found that we need to formalize it. So we went into calling it as Emerging Open Tech Foundation, and it's established as a uh, what do you call uh, social purpose organization out of Mumbai, Thane, and we have had several presentations prior years, even during COVID and all, for the uh, national uh, mission um, in the Indian context. And we are here in the Silicon Valley. Our roadmap, even though, is pointing to India and Linux and connected intelligence and transition to 5G and quantum leap. So our connected intelligence is what is our goal, and we have been operating on this. The links are here for our EOTF, where you can find what quantum we are focused on, the charter, etc. And the tiny URL is the one which is the one related to our quantum computing, Santa Clara Quantum Computing Group, which is established hardly 2 weeks back. We have other groups, but this is the one we are focusing on quantum. Coming to what is quantum computing, because the fact is that okay, we do computing, but how is it different? So quantum computing is very similar to classical computing, but it's not deterministic model, it is more a probabilistic model. So 0 and 1, what we use binary here, 0 and 1 are probability, and the sum of the probability is 1. So that's how this is more of a probability. You can use the continuous or a discrete, and this is more analog than discrete, but we use discrete level. So there are some challenges here that you can figure that out, but there are advantages to it. Otherwise, why would somebody do it? It's must multidisciplinary because it's ideal for it deals with subatomic particles. So to leverage a computing paradigm at that subatomic level, uh, even the Einstein struggled for it, and finally it has taken almost 100 years when David Deutsch, and then finally uh, uh, it has come to somewhat of a around 2010, the first computer were quantum computers were produced by Lockheed Martin here in the valley, and then on the chase has started. So quantum phenomena is can be visualized both at the particle and wave nature. So if you have a electron or a proton or a neutron or whatever subatomic particle, their energy levels move, and normally semiconductor we talk about the Fermi level for the metal and the semiconductors and how they move and all that. But the nature here at subatomic particle provides us ability to do parallel operation. Humongous. So instead of reading line by line, I can read the whole book. And that kind of a capacity quantum computers brings to table. And that is possible only because of it is being at the subatomic level, and you can do single um, atom or a single uh, subatomic particle to do one operation. And so, if you know of the chemistry, Avogadro's numbers in the order of 10 to power of 24, that you can understand that how many you can bring together. So the applications of these are in various for usually solving uh, uh, unconventional problem, I'll put it, because on conventional computer you talk about the polynomial uh, way of completing like prime number factoring and all that. So this is NP, they call it NP hard problems is what in computer and communication it handles. So quantum computing as such is more of a subatomic probabilistic model of computing, which is leveraging uh, natural characteristics of quantum. Now, here is a chart which represents what classical computing is and what quantum computing is. Representation wise, you use 0, 1 bit with a voltage level for classical, whereas for quantum computing, you represent through bits. They are called as 0, they are called as states. So cat 0, cat 1, as I they are represented as some qubit states, which we will explain later. But at this time, we can assume that they are not binary or they are not decimal, but they are some abstract states. So you can go from one state to another state, or you can be somewhere in between the state. So that's the reason representation is in terms of state. Operation, if you look at classical computing, they use Boolean algebra to do all this arithmetic logic it uses, but in uh, operation is done using superposition, entanglement, and interference is what matters in the case of quantum computing. So you'll hear the quantum processing unit corresponding to that. So operation are done using QPS. Logic gates wise, you can see in classical you have got either a reversible, non-reversible. That means you say two input, one output, so there is no way to reverse, right? Because you have already merged the two and you got something 0 1 0 or 0 1 2 1. It's not reversible. Whereas quantum computing is unitary, gates are used and they are all reversible. So, like example, Fourier transform and inverse Fourier transform. So, if you can go forward, you can go backward. So, communication is one of those logics, and there are different gates than what is existing in the classical. Robustness, of course, the uh, so I have to say that 300 degree Kelvin is the temperature, which is the room temperature or normal temperature, what we call 17 to 20 degrees centigrade, or approximately some 50, 59, 60 degree Fahrenheit. Uh, now, this is the classical computing where we operate at almost normal temperature. Whereas in quantum computer, you have to run the computer hardware at millikelvin level. So that is like minus 400 or minus 300 Kelvin and below. So we call it millikelvin because it is absolute zero temperature plus some millikelvin, maybe operation at 10 millikelvin, 4 millikelvin, or somewhere around that. So this is very under very cool temperature we operate. Measurement, of course, everything is deterministic, so you can copy anything and then you can carry forward in classical computing. But in quantum computing, there is no cloning. You cannot copy anything because if you try to measure, it will disappear because coherence is an important factor, and that's why you call it statistically. So quantum computing is different in that sense that you have to uh, what you call you have to put the input, whatever input you give, which is generally classical, a bit, and then you apply a state to it, and once the state is there, you have to transform, and then you get the output, and then you have to measure it. If you try to measure it, it will disappear. So you have to infer in a way so that the operation can be successfully carried out. So there is some similarity, but some dissimilarity here. Very, very important similarity because you can't clone. So if you take a qubit, you cannot clone hardware. Now, hardware is something you can use a diode, transistor, binary gates, MSI, LSI, LSI, binary systems. Many. So binary gates are easy, but in the case of quantum computing, we use different type of materials and hardware. Like you got trapped ions, you got Josephson junction. These are nothing but metal oxide semiconductor at the low temperature level, and so that you inference can be made by measurements or so that there is uh, distinction in the probability that it is a 1 or a 0 state or something of that kind. So the hardwares are very hard and it's based on electronic spin. A spin up, a spin down can be spin up can be a 0, spin down can be that's how. And they are not just 0 state; they can be 0 and 1. So the power of computing is in the case of classical computing, you can process n bit like 8-bit computer, 16-bit, 32. You can do one operation at a time and sequentially, or you can do parallelly. Still, it will not be fast enough even for. Whereas in comparison, you can do for a n bits, you can do 2 to the power n. So if I have a 10, then I can do 1000, 1026. If I have 2 to the power, let's say 20, and then similarly it will keep on going. So exponential computation capability is there, which is what kills classical computer by leaps and bounds, and we call it quantum leap sometimes. So these are the classical to quantum computing differences. We'll go over it over the 18 weeks, many more to learn. But at the high level, if you look at the abstraction, this is like a stack, like we talk about full stack. The quantum hardware is the analog hardware, which is at the bottom, and it has to be probabilistic model. And above that is the operating system. The operating system of the classical computing will have to be appended with computing like spin, swap. There are very instruction set. All these instruction set are architecture has to support ISA, has to support the quantum uh, language and controls. So there is a special uh, whatever the instruction for that have to be compiled, and then you have a framework of quantum computing along with the quantum algorithm and the application. So applications drive the algorithm, algorithms drive the framework, and the framework has input output based on classical, but at the same time, sorry, the compilers compile it and then are interpreted with the control units which are quantum, and then operate with the operating system with the quantum hardware, which is the cryogenic example is one of them. So superconducting quantum, we call it CQ, is one of the ones. There are many other forms like using photons, using ion traps, several things which we use to provide the high level of abstraction to complete the full stack. Moving on, there are many applications. The earliest one looks like is like a quantum cryptography, which is like your Y2K. There is a Y2Q. So as soon as quantum computing comes, it will break all the security and it will create hell. So there is a mandate which is being proposed in at least in US called Y2Q, which will happen next 2 3 years once the NIST settles what the lattice algorithms they selected will be finalized and tested and all that. So this can be used for computational chemistry and modeling, can be used for forecasting with the genomics, machine learning, simulations and all that, like your twin cities, like twins, right? So digital twins you can do with simulation. So there are many of these, and since as part of our emerging open technology, we have been focusing on the what do you call as sustainable development goals. So part of the sustainable development goals uh, can apply quantum computing, like healthcare, like we saw in the COVID-19, then weather monitoring. Infrastructure in itself requires quantum is beyond high performance computing. There is a lot of hardware involved, so there is a need for development. Then you got sensing applications like MRI, then Y2Q, which I mentioned. The people have got like 10 years back, it was said that it will be done 10 years, and 10 years from now, we'll say that it will be done. So there are different opinions, but this is evolving in such a way that it's definitely now next 3 to 5 years, we are going to have a full-fledged commercial, which is already started by some of the companies, and then defense is already utilizing it and attempting everything. So quantum logic circuit is what you see. This is one very important thing, and satellite communication will be used, like example for key distribution, telemetry, etc. So many applications are there, and quantum sensing is the low hanging fruit, we can say, because already you see quantum. First, one of the weakness of quantum is that it coherence and incoherence. So it decoheres. That means it can. So if you ask somebody how long you can run a quantum computer, I would say millisecond is the max. So within millisecond, if you have to do millions and billions of operations, yes, that's what it is. So the question is, if that is the weakness, to be exploited for sensitively identifying what can you sense. You can sense at a very high accuracy level. That is why you will find that this is being uh, applied to a lot of other sensing applications, including weather, agriculture, soil, water fertilizer, fertilizer management. And so sensing probes with a quantum uh, phenomena can be used. And they can also be used in the devices, smaller devices, as well as for us to be able to get the massive computation. It can be also combined with high performance computing. So there are sensing applications in medical and agriculture, which have, and even in finance, which have come up as very important. And that's one of the areas of focus. So what are we going to do? That's the question, big question. And the biggest answer to that is simple. We are going to cover quantum computing fundamentals like any digital computer fundamentals we do. We call it as QFC 101. There are three parts to it. First part, we'll try to cover the computing and the information communication because computer and communication merge in this. That's very important. And electronics comes in because you have to control the logic like any other, but with a different gate circuit. So we call it as qubit circuit logic. And so the control, we control the backend. Backend can be anything. It can be many of the electronics, as I said, supercomputing, ion cube, um, ion cube, and similarly some of the other like photons, or charge, or flux, or magnetism. You can name it. This is a science to technology. There is very applied science basically. So you got different mechanisms to control it, to change the level of energy, entropy, what we call, and there, that's what the thing will be in the part two. Part three is more towards algorithm. Obviously, there are grower search algorithm, and you've got the other Shor's algorithm for prime number perfecting. These are the two major. There are many more QA, OA, and all, but these two we will try to cover because that will give us the computing acceleration as well as communication multi-channel uh, uh, transmission of the what you call entangling of bits and teleporting and all that. Those we'll explain later. But for the time being, assume that these are the things, and this may be 2 plus 2. There is algorithm might be split further, so we may have 3 or 4 parts as we go. And we have 4 months, so you can cover 4 topics. First month fundamental, second month quantum circuit, third the communication algorithm, and computer algorithm. So 4 weeks we can cover. 4 months we can cover. Each month will be 4 weeks, so approximately 16 weeks, and 1 week in the beginning, 1 week in the end. Like this is the first week, so 18 weeks we want to complete, and this is a reasonable pace. The reason is if you do any of the quantum computing courses, it will take at least 3 months if you are a beginner. So this is fair enough for us to be able to cover beginner as well as intermediate, and we have gaps between the classes to be able to with. Going forward, here is the resource list. We are sharing this with you so that you can start building it. And we recommend the Dr. Yu Wang, who is the professor, current teaching professor, quantum computing at uh, San Jose State University. He is a professor from Berkeley, and so he has participated in quantum uh, building, computing building for several years, and well qualified. And quantum computing is definitely confusing because of the math involved, because of the metrics involved, vectors involved. So it will be easier to go through a single standard book, which is recommended. If you are not able to purchase, that's okay. We have still the links from UC Davis and MIT, which is publicly available. So, uh, but we will try to adapt to a single, uh, whatever the notation which we call as uh, uh, the cat notation, cat 0, cat 1, that we'll explain as we go. But state presentation is important. There are glossaries available from IBM. Also, we will be talking about the ability to use Python, Qiskit, and ability to do some of the other uh, things. So I think this is exhaustive. We'll be able to look at it. And, so one very important quote from Richard C. Feynman, who in 95 around that time, because quantum is always evading, has been evading. So we have to be realistic. For successful technology, reality must take precedence over public relations. We are not doing any publicity or public relations because we cannot fool the nature. We need to adopt natural phenomena with a synthetic quantum uh, phenomena, which we want to bring into electronics or superconducting quantum, etc. So it is hardware is the barrier right now, but simulation is not a barrier. So we can use today everything. As soon as the hardware is built, all software will be applicable. So it is better to focus on software if you are generalist, and if you are a particular hardware specialist, then you focus on the superconducting all the hardware stuff, logic and all that. Otherwise, at basic level, you should be able to understand this and adopt it for future as we move to the era of quantum. So that is all I have, and I will, with that, hand over to Professor Gokhale. Gokhale sir, are you there?
Thank you, Prakash. I'm here very much. So kindly permit me to share my screen.
Yeah, I'll stop sharing.
Yeah, give me a moment.
Yeah, sure.
Oh, okay. I think I'm live.
Yeah, start sharing.
Yeah. Yeah. Is my screen visible, Prakash?
Yes, absolutely
Oh,
perfect.
thank you so much. Thank you so much. Thank you, Prakash, and you have done a good job. A wonderful context that you have set, goals and the deliverables for this entire workshop, the training program are very clearly set. And I'm Jayanti Gokhale. I'm signing in from Mumbai, India. And I'll be also partnering with Prakash to deliver the topics which are listed out over the next 18 weeks. Today, what I'll give you is a very, very quick overview. It's something like a bird's eye view about what we are going to cover as part of this module. So, I'll be speaking in general about what are the core features of the classical computing mechanisms and how what exactly we mean by shifting over to the quantum domain. What exactly are the advantages which we get over the classical computing paradigms. We will quickly make a mention about the quantum properties, and we will also as we move forward, we will look at what we mean by the particle and the wave duality. I'm not getting into the physics aspects, I'm not getting into the quantum mechanics per se, but I think it is good if we just have a small appreciation to these fundamental aspects. A core to quantum computing is a phenomena called as superposition, and superposition essentially allows you to think in parallel. And whenever you talk about picking up any application and then trying to implement it on a quantum environment, the parallel approach of decomposing a problem is something which is inherently essential. So, towards that particular context, we will understand what is meant by superposition and a behavior in terms of how these quantum elements work. And together with superposition, there are two other aspects which are also pretty important. The first one happens to be what we call as an entanglement. Now, this entanglement essentially gives you a mechanism where we talk about interdependencies on the interactions between two or multiple quantum entities. So, we'll be talking about that. Sensing is something which Prakash already had made a mention. And as we move forward, we will also quickly look at what exactly how the quantum machine from IBM looks like, and what exactly is the way we build up the interconnects and the interfaces and stuff like that. So we're going to get into a few of these particular topics today. So let's get started with a core introduction to this entire gamut of quantum computing. Firstly, we know the fact that quantum computing mechanisms and paradigms are totally and radically different from the classical approaches. And what do we mean by classical approaches? The conventional way which we are already aware of, the conventional approaches which we are using both at your laptops and maybe even your supercomputers or even processor that operates in your mobile phones, essentially this mechanism is now identified as a classical computing mechanism. And in a classical computing world, we have information represented as binary digits, uh, very clearly identified states, which are also modeled as the zero state and the one state, usually represented by some electrical phenomena that is measured, something like a voltage. And there the entire state is highly deterministic, right? And we have got computational models, algorithms, mechanisms built around this entire binary implementations. You've got state machines also to process the data. When you come down to quantum levels, you on a similar mechanism, you identify a subatomic particle's behavioral state. And that particular behavioral state is modeled. Let us say we just typically take a simple atomic state. And if at all you look at the spin of that, maybe spin in one direction could be modeled as a zero. Maybe we call this as a spin up. And a spin in the absolute opposite direction is modeled as a one. We call this as a spin down. This is fine. So you just look at the atomic level behavior, and if you just look at the spin models, and the spin models can give you a 1 and a 0 representation of the state. But if you look little more closely, if at all you want to check out what exactly is the current state, it becomes very difficult to observe. So when you get into the current state, you have to get onto observation at a particular point, and at that particular observation of a particular point, you will notice the state to be either a zero or a one. But while in operation, this unit, we call this, let us say, as a quantum unit. This quantum unit could be in a bunch of multiple states uh, between zeros and ones. And when you want to notify this, you typically have to bring in a probabilistic model. So you say that, okay, currently it appears to me that the state of this unit is a 1 with a probability of 0.65, which automatically means that it is in a state of 0 with a probability of 0.35. And this probability once again changes maybe the next moment. So what do we mean by this? So you have now a device or a unit. When you observe, you just notice the fact that it is either in a zero state or in a one state, but it also could be in a whole range of intermediate states. And this range of intermediate state is what is modeled in context of a probabilistic behavior. And so this gives you an opportunity to say that, yeah, I have got now a device which can present itself in multiple states, not just only two states. And that gives you a very great computational power. So now the question is, how many discrete probabilistic levels can I observe? Once again gives me a situation of an advantageous position of having a multi-state type of a device, the quantum device. Incidentally, these quantum devices and the entire scenario of setting up information representation is modeled as what are called as quantum digits. And quantum digits are also called as qubits, quantum bits, right? So the reason why we call this as a quantum bit is still at a fundamental level, it is either a 1 or a 0, but augmented with a probabilistic behavior which could have an intermediate value between 1 and a 0. Right. So when you look at this quantum computing, essentially there would have to be some mechanism wherein you have these devices operating, and these are subatomic type of particles. And the subatomic type of particles, the energy levels therein is what is, let us say, monitored and measured and controlled. Right. So these subatomic level particles could be coming from various implementations. Could be at an atomic level implementation using photon implementations, charge implementations, flux based implementations, and so on and so forth. There are multiple implementations which are there, but fundamental to all of them is implementation of what we call as a qubit, right? So how do you energize these qubits? So these qubits are somehow realized, and you have got media that is there to set up a stable environment, and these are excited. right? And the moment we talk about an excitation, once again, appropriate excitation is what is subjected out there, and that causes the so-called state transitions to typically happen. So the units could be moving from a level 0 down to a level 1, or level 1 to a level 0. So these sort of transitions typically can be realized in a controlled manner. And as I mentioned earlier on, it is not just only a critically a transition between 0 and a 1, or a 1 and a 0, but there could be a whole bunch of intermediate ranges of the state, and that is the exponential computational power which you gain with quantum devices. We are going to talk a little more about this as well, right? So, how does this quantum computer actually look like? So, the picture you see on the right is essentially IBM's quantum implementation. And this IBM quantum's implementation has the actual quantum processor. I'll just show you a sort of a picture of that close up. And these phenomena, as we know now, have to be handled at extremely low temperatures, typically millikelvin level type of temperatures. So for that, the most of the infrastructure is all centered around uh, some form of cooling mechanisms. These are called as helium isotope cooling mechanisms. These are handled by a um, bunch of what do you call compressors and pumps and associated control systems and monitoring critically these extremely low temperatures and all of that. You have got a whole bunch of paraphernalia built around that. So most something like it's a huge, massive refrigeration unit, which ensures the fact that these quantum elements are operating at that so-called millikelvin level of a temperature. But the reason why we have to do it is, these devices are absolutely sensitive to A, the temperature variations, B, the thermal shocks and thermal noises, and also electronic interferences, electromagnetic interferences all around. Right? So all this sort of shielded environment is what needs to be created. So whatever you see in picture is a whole bunch of that infrastructure together with the communication infrastructure. Remember, the activity that happens on the device is for a very short period of time, right? Maybe a few milliseconds or even a few microseconds. So the phenomena has to be observed and recorded during these very small intervals of time, right? So you require to grab and capture extremely large volumes of data or information during a very small period of time. So the essentially the type of communication bandwidths that are required normally are realized using fiber link ups out there. Okay. So how does a user run a program? So we use a quantum processing unit. So out over here, central, you can just see my arrow pointing out over here. This unit is the actual processing element, the central processing unit. Instead of calling this as a central processing unit, now we call this as a quantum processing unit, or a QPU per se. So this QPU is accessible, right? If at all you are just sitting next to the QPU, obviously you just have a mechanism by which you can just pump in your program. Or nowadays, let's say IBM and other companies, you have got different type of implementations coming from various organizations. I'm just taking an example from IBM. Uh, these machines are accessible as a cloud service, right? So you have got a bunch of tools which allow you to set up your application and then fire a job through a cloud service. And the moment you do that, the environment out there uh, typically translates your job code, whatever is the application which you have written, and it translates that into a whole series of orchestrated triggers that allow, reconfigure, and modify the so-called quantum gates, right? And those are once again done at a subatomic level using some microwave type of interactions, and the responses once again are captured, right? The responses generated by the qubits are captured, and these are called as the readout values, and those readout values are once again picked up by the so-called sensors out there, and they are once again converted back and translated back into some sort of a binary values which are given back to the user. So understand this, programming this device essentially has to be done in something which is more comfortable at our level. Maybe we'll have some sort of a programming language and an associated bunch of libraries, or we could have a typical representation of the interconnect patterns of the qubits identified and denoted by a maybe a tool. And once we have defined that behavior from our applications perspective, there will have to be some sort of a let us say a runtime engine, or maybe some sort of a backend resource that will convert this into mechanisms that will trigger operations to be carried out on the physical quantum processing unit, right? So, a very quick comparison about this classical computing and the quantum computing paradigms. Prakash gave a very wonderful introduction, so I'll just reiterate the same aspects out over here. So when you talk about, let's say, a classical computing, there the information is represented with a 0 and a 1. We call this as a bit representation. And then you've got a whole bunch of operations which are defined over these bits, bit 0 and a bit 1. When you come down to quantum, you also have got a similar representation. You call this as a qubit. A qubit is also denoted by a 0 and a 1. There is a slight difference in the way we typically talk about the representation. So don't worry about that representation which is showed out there. Things will be uh, made very clear a little later on. So this is a different type of a notation. We call this as a bracket notation, a representation. We'll talk about that. But in addition to that, we have got a state which is called as a superposition. So that is the reason why you see that plus sign out there. So you have got two basis states, as we call it. These are the so-called orthogonal states. Once again, pardon me for using these terms, but these ones will be made very clear in the subsequent sessions. So I've got two basic states, the 0 state and the 1 state. These are called the basis states. And then you now talk about a state which is a combination of both these two states. And that is what is also meant by the superposition. Superposition applies and then tells you what exactly is the intermediate state or a current state, a probabilistic state values, right? So that's the way information is actually represented. So the information representation is a little different than how we know in the classical world. Classical bits, we know clear phenomena in the context of Boolean algebra, Boolean logic, and state modeling and things like that. Uh, in similar lines, with respect to quantum computing, we have got three core phenomena called as a superposition, entanglement, and interference. We're going to talk of all of this in much more details with respect to the mathematical representation and what is the way the phenomena is actually realized using the so-called gates. We'll be talking about the gates, very much like we have got the AND gate, the OR gate, the NOT gate, the NAND gate, and the NOR gate. Also, the exclusive OR gate in normal binary domain or the bit level domain. We also have got a bunch of gates in the quantum domain. We'll be talking about that too. Um, the basic difference in quantum computing is that all these devices are essentially unitary and reversible. And what do you mean by reversibility? They're going to have a formal look into that. But for reversibility, uh, gives you a mechanism wherein, given the output, it is always possible for me to critically determine what exactly were the inputs. Whereas, in a classical computing, your conventional gates, these are not reversible. We'll be talking more about that. And reversibility is one very important criteria for even observability, and that will be the fundamental paradigm under which quantum devices, quantum units are assembled together. They are going to be completely reversible in nature. When you look at how these devices operate, uh, in a classical computing models, these devices, whatever are the gates, your CMOS gates, your NMOS gates, are highly sort of immune to noise. So you've got gate implementations which can work anywhere from, let's say, minus 15 degrees centigrade all the way up to maybe even 50, 60 degrees centigrade, room temperatures and stuff like that. So devices can operate at a so-called real world environment as we see. Whereas when you look at quantum computing, these are absolutely sensitive to noise. Maybe the noise could be your any electrostatic noise, electromagnetic noise, right? Thermal noise. It is absolutely sensitive to all such noises, and because of this, it has got a low level of fault tolerance. So we need to ensure the fact that these devices operate at uh, what do you call millikelvin type of temperature ranges, so that the thermal noise can be brought down, and the atomic level interactions can be observed, right? So this presently the devices are absolutely sensitive to noise. So this is one of the big challenge in terms of getting a quantum computing to work. Hopefully, maybe over the next few years, we might be having a quantum computing environment which probably can fit into your laptop type of an environment. Laptop also has got a processor and it has got its own uh, cooling mechanism. So maybe, who knows, tomorrow we might also get such devices which can have cooling mechanisms which are good enough to operate in your normal standard open air environments. Uh, as far as observing the state, right? In classical computing, the devices which currently we know, the state can be copied, and they are absolutely deterministic. I think Prakash made a clear mention about that. Whereas in quantum computing, there is absolutely no way to copy that. So there is no cloning that is possible, and the uh, measurements are purely statistical in nature. Probabilistic measurements are there, not pure deterministic type of measurements. Realization, uh, you have them in the form of a transistor that could be using any of the technology, but the transistor happens to be one of the fundamental switching element that is used using any of the technology, the silicon and the semiconductor technology. Whereas the moment you move over to quantum, you got different implementations that people are trying out, and like the superconducting implementations, Josephian junctions. You have got some photon-based implementations, charge coupled, charge control devices, ion trap. Right? So you have got various techniques. Companies are having different approaches to sort of implement these sort of fundamental devices out there. And where do we actually gain in the context of quantum computing? Uh, if you look at classical devices, you have all these computations typically perform one bit at a time. So it's basically a one bit at a time, and you could have a n word data element there. You can typically perform the operations. Whereas out over here, you're talking about multiple states for each and every individual element. So if you just say that you have got about, as Prakash was mentioning, let's say 10 states, you can now talk in terms of 2 raised to the power of 10 different intermediate states per element. So you have got a large number of states that you can exploit in terms of implementing this, and all of this now will happen in parallel. So this is a picture which typically talks about what is called as superposition and an entanglement. I'm not just getting into the core details. We'll just have this for the uh, as a topic of discussion in the forthcoming session. But what superposition is all about is as follows. Now, superposition is a wonderful concept that has been used and that is currently also being used. And what does it essentially say? If at all you have got some, let's say, a phenomena which can be partitioned, which can be bifurcated, which can be subdivided into its basis components, and if at all I can identify the outcome or the behavior of a system to each of these components separately, I can combine all these responses together. So that's a fundamental way by which your Fourier behavior is also modeled at, right? Given a typical system and subject the system to some input, let's say signal. If the input signal can be decomposed into its basis component signals, I can identify the system behavior to each of these component signals as individual responses which can be recombined, right? That is exactly what is superposition. On similar lines, we also have got superposition that is used up out over here in the context of the spin depiction of the, let's say, the subatomic particles, right? So I can talk about two distinct states, the zero state and the one state, and I could also now talk about uh, maybe a bunch of intermediate states, somewhere between zero and one, and these could be now modeled as, let's say, components of two orthogonal base states, right? Components of two orthogonal base states, and that gives me a representation which is something like a complex sort of a representation. It's not a pure complex representation, but something like a complex representation. Something like I say that, okay, the current state could be, let's say, 0.65 probability of a 0 and a 0.35 probability of a 1. So I just have a combination of both these two influences as two different components which are recombined to determine the state. So this is what is called as a superposition. Don't worry if it is a little cryptic right now. We will demystify this with some elementary math. You don't have to worry. We are not going to talk too much of math also a little later on, but I think we are going to make use of some basis math. And as long as you know what is meant by vector representation or maybe a array representation, we will now talk about representing this phenomena using some core elementary math, and we will also talk about some basic math operations like vector multiplications and matrix multiplications, and then we will talk in terms of how to represent a tensor. So tensor arithmetic, we will talk about that. This is once again fundamental to the understanding of this entire behavior, but I'll take this up slowly in the forthcoming sessions. So that's about superposition. And what is entanglement? Entanglement is something like this. There could be now, let's say, two qubits and they are coming together. So when two qubits come together, probably they would have their own basis states influencing each other. And it so happens that both these two influence each other. They could also have a very nice royal dance that could be there, or they could unify themselves in combining towards a common direction, either the up direction or the down direction. So this is essentially what is called as an entanglement. And once again, when two or more qubits can get mixed up, then we once again have an indeterminate type of state. So that is once again needed to be modeled. If both of them are in the same phase and in sync, maybe it just gives up a enlarged view. It gets you an amplification. Whereas if something like two wave properties or two wave mechanisms, if they are something like an out of phase, they combine them together. You just try to see the combination realizing a negated type of a response. a degraded type of a response, a deflated type of a response. So either an attenuated type of a response or a deflated type of a response is what can be realized because of this sort of an entanglement. So once again, we'll talk about this phenomena also in a reasonably greater detail as we move forward. Remember, I was talking to you also about this reversibility. This is something, once again, pretty very important to understand. In quantum implementations, we always make use of these qubit representations, and every qubit is supposed to be, let's say, reversible. Or in every gate which we define has to be reversible. The quantum gate, we are going to come down to the quantum gate. Like we have got your binary gates, we have got quantum gates, and these quantum gates have to be reversible. And what do you mean by reversibility? If at all I identify an output, I can exactly identify, determine what exactly was the input that caused this output. So the cause and effect relationship is very critically defined in the context of reversibility. So which also means the fact that if there is a device which has transitioned through a whole series of states, if I am now observing the current state, I can trace back to find out what exactly was the initial state. Now, that is possible when the device is said to be reversible. Now, binary logic devices or binary logic gates are not reversible. For example, if you look at even an AND gate, right? The moment you say that the AND gate output is, let's say, a 0, you cannot critically determine whether this is because of the fact that the inputs were both zeros or one of them was a 0. And if so, which one? You cannot really determine that. So that is the reason why we say that binary logic gates are non-reversible, right? So we are going to use these quantum gates, and every quantum gate is modeled to be reversible. So we will be once again using these fundamental paradigms when we set up a network. That's how we do, let's say, building up our programs as well. So how do we do the programs? Yes, indeed, we need to program very much like we have to program your classical computers. We need to also program our quantum machines. So how do you do that? Uh, you can just pick up some software simulators. There are some software simulation tools where they have a random generation that works in the backend, and that random generation will typically give you the so-called modeling of the superposition, the intermediate random state. These are software simulators which are available. There are cloud services which are also popular, and these cloud services operate on the core physical backend. The backend, the actual machine is there, which can be programmed, or they also have got a simulated backend. So both these two are available. So cloud services are available, and most of these biggies are offering these sort of cloud-based services, including IBM's and I think all the other people as well in the market. The third way is, you can also have a circuit simulation in silica. So something like you can have a VHDL or a VLSI type of a simulation of this sort of phenomena is what is also possible. Maybe you just typically talk about a 128-bit register which can be randomly triggered, and that particular random state can be used as a representation of a superposition state. So you have got circuit simulation also available to in silica, right? So this is what exactly is the infrastructure. And coming down to the programming, you can get started with writing down program, which is like an assembly level bunch of instructions. So every quantum processor is defined with respect to its bunch of instructions, and you can set up your so-called program, or we also call it as a network, and then write down these assembly level instructions. Okay. Sometimes it is also possible for you to embed these in the context of a very well-known programming language, something like Python, right? The other scenarios which are available are essentially some visual tools or block based programming tools. So you have got a front end, you can have a visual interface, a GUI based environment, drag drop, and then you can create your own program and then get out to running that. Right. So you have got even block based approaches, which are visual programming tools, which are available. So we'll be using a bunch of this as we move forward for our implementations and understanding. So quantum computing essentially is that particular area supposed to be showing a lot of promise of the futuristic type of a computing paradigm, and hopefully we will be seeing a major transformation in how we look at computing, and this might also bring in a whole range and a whole array of alternate programming paradigms. You can use this link, and we have set up a small library of resources. You can just access those resources, click on this tiny URL link, and then you can just get a bunch of resources which we have put up out there. And these resources, we are going to augment it as we move forward. We're going to add up all available material which is of use to the community. All of that would be made available out over here. We call this as a QFC 101 library. There is a small assignment which is also given out there, and a small survey link. Kindly click on the survey link and then kindly participate on the survey as well. Coming down to the lab, we are going to set up a lab. We are going to guide you through this entire process, and then we are going to take up a few participative exercises. And lab references are also mentioned here. And most likely, we are going to use IBM's QuizKit, and the references for that are also available in https://quizkit.org. And it's also a good time to quickly review Python and the Jupyter environment. So the references for that also are presented out over here. Uh, Let us see as we move forward, whatever is comfortable, whatever resources are possible, we are going to make that provision here, and then we will have some form of a practical implementation also of a few of the phenomena. So in summary, quantum computing is all about manipulating mm, elements at a subatomic level, and ensuring the fact that these devices exhibit their state properties, not just only the so-called binary level of a state, but we talk about multiple intermediate levels that gives us a potential capability of an exponential power of computation, right? So here we talk about carrying out multiple state level operations that can be done in parallel. When you want to actually build or realize this quantum computer, this is not an easy task. It's not that you can just go on to any shop, maybe pick up a few elements and then fix it up at home and then create a machine. No, it cannot be done that way. Uh, it's not a very trivial environment that you can create even in let's say small enterprises. So it's a it requires a lot of additional infrastructure, essentially because of the uh, fundamental inherent blockages to the fact that it has to operate at millikelvin type of temperatures. So it has to be done in a properly created environment, and that is something that is the more, what do you call, the cause for or a challenge, I should say, a challenge that we are probably likely to look at in the next maybe 8 to 10 years, to ensure the fact that these devices probably can be made operatable at room temperatures. The fact that every element can operate at multiple states gives you maybe a feeling that it can be used in solving hard problems, computationally hard problems, right? A computationally hard problem, a problem which normal classical machine would take a few days or maybe a year to solve, hopefully can be solved within a few seconds or a few minutes on a quantum computing environment. So that essentially is what we also talk about. So that sort of a promise is there, and then with that promise, I think we are all set to go move forward and learn more about this entire quantum computing and the way we can typically get into this new field. Our entire course is essentially based out on this book, Introduction to Quantum Computing. The book is referred out over here, and I think the resources also have got a PDF version of this, which you can possibly download and then have a quick understanding. For those of you who are interested, you can also uh, buy it. Next week, we are going to talk about what is meant by quantum computing. We are going to demystify all the terms, give a small mathematical background, and then critically get into all the topics of what is superposition, what is entanglement, and how do we represent these qubits, what type of interactions are realized. All of that will be initiated from the next week. If you have any questions, floor is open. Myself and Prakash will be happy to handle your questions. Thank you very much.
Hi everyone. We can go into the Q&A session. Thank you.